Have you ever stopped to think what a simple piece of metal has in common with, say, the smartphone in your hand, or the speed of a chemical change? Well, today, we're going to connect those dots. We're going to explore how the world around us is powered by some truly incredible chemistry.
Okay, let's just dive right in with a question we've all probably had at some point. How does a battery actually work? To really get the answer, we have to build the story from the ground up, starting with the very elements that make it all possible.
So, to kick off our story, we first need to meet the main characters. These are the fundamental building blocks, the incredibly versatile elements that play a central role in, well, everything from energy to catalysis. Let me introduce you to the D block elements. You probably know them as the transition metals. If you picture the periodic table in your head, they're that huge block sitting right in the middle. We're talking about household names here, like iron, copper, zinc, and silver. These guys are the true workhorses of the elemental world. So what makes them so special? Well, these elements have a unique set of skills. For instance, they have variable oxidation states, which is just a fancy way of saying they're not picky about how many electrons they gain or lose. This makes them super flexible, chemically speaking. They also have catalytic properties, meaning they can speed up reactions without getting used up themselves. Plus, they form these beautiful, colorful compounds and even have paramagnetic properties, which means they're weakly attracted to magnets. It's this chemical Swiss Army knife of abilities that makes them so crucial for everything else we're about to talk about. All right, so we've got our key players, but how do they and other elements actually interact? You see, in chemistry, it's not just about if a reaction will happen. It's also about how fast it happens. So let's uncover the secret of reaction speed. This brings us to a field called chemical kinetics. You can pretty much think of it as the official speedometer of chemistry. It's the science that measures the exact rate of chemical reactions, and this is the important part, it studies all the factors that can make them go faster or slower. So, how do we actually put a number on that speed? We use something called the rate law. Now, I know it might look like a little bit of scary math, but the idea is actually super simple. It's just a formula that tells us exactly how the amount of stuff we start with, the concentration of our reactants, directly affects how fast the reaction will go. And this table shows it perfectly. Reactions kind of have different personalities when it comes to speed. We classify them by their order. So for a zero-order reaction, the speed is just constant, chugging along. For a first order, the speed depends on the concentration of one thing, and so on. This also changes their half-life, which is just the time it takes for half the stuff to get used up. Okay, so knowing the speed is one thing, but the real power in chemistry, the real game changer, comes from answering this next question. Can we actually take control of this speed ourselves? And the answer is a big, loud yes. So let's look at how chemists can basically hit the gas pedal or slam on the brakes to manage the pace of any chemical reaction. The key concept we need to understand is activation energy. Think of it like this. You've got to push a sled up a snowy hill before it can slide down the other side, right? That initial push you need to get it to the very top, that's the activation energy. In chemistry, it's the minimum energy boost molecules need to actually react when they bump into each other. So, if you want to make things happen faster, what do? You find a way to make that hill smaller. And that's exactly what a catalyst does. It's like a chemical shortcut. It creates an entirely new, easier pathway for the reaction, one with a much, much lower activation energy. So the reaction speeds up like crazy, and the best part is, the catalyst itself doesn't even get used up. And guess who the superstars of catalysis are? Yep, you guessed it, our main characters from the beginning. Many of those super versatile D-block elements are absolutely fantastic catalysts, and it's because of their variable oxidation states. That ability to swap electrons so easily lets them grab onto reactants, lower that energy hill, and then let go of the products, ready to do it all over again millions of times a second. Okay, so we've got our elements, we know how to control the speed of the reactions. Now for the final act, where we put it all together. How do we turn all this amazing chemistry into the electricity that powers our lives? Welcome, my friends, to the world of electrochemistry. This is the incredible field of science that's literally the bridge between chemical energy, the energy stored in molecules, and the electrical energy that flows through wires. And the engine that makes this conversion happen? That's the electrochemical cell, sometimes called a galvanic cell. It's a clever little device that's built to capture a chemical reaction and turn it into a focused flow of electrons. And a flow of electrons is, you got it, an electric current. So here's the million-dollar question. How do we know if a cell will actually make power? It all comes down to whether the reaction is spontaneous, which just means it wants to happen all on its own, releasing energy. We can measure this. If a value called the cell potential, or E cell, is positive, it's a go. The reaction is spontaneous, that means it releases free energy, and that's exactly what you want inside a battery. Let's bring all this back down to earth now. We see the ideas of electrochemistry absolutely everywhere, in the batteries we use every day, in the rust we're always trying to stop, and even in the future of clean energy. Here's a perfect example you've definitely seen: the rusting of iron. There's our D-block element again. It's an electrochemical process. You can literally think of rust as a very, very slow, messy, and totally unwanted natural battery, where the iron is spontaneously giving its electrons away to the oxygen in the air. And this brings us full circle, right back to our original question. A battery is just a really well-designed electrochemical cell. It takes a spontaneous reaction, forces the electrons to flow from one end, the anode, to the other, the cathode, through a circuit. And that flow, that is the electric current that brings our phones and laptops to life. So, what's next for this technology? Well, say hello to the fuel cell. This is a really advanced kind of electrochemical cell that doesn't store its energy inside like a can. Instead, you just keep feeding it a fuel, like hydrogen, and it converts that fuel's chemical energy directly into electricity whenever you need it. And the advantages here are pretty incredible. They're super efficient at turning fuel into power. They can be almost completely pollution-free. I mean, imagine a car where the only thing coming out of the tailpipe is pure water. And because there are no big moving parts like in an engine, they're basically silent. All of this makes them a seriously promising technology for our energy future. So there you have it. From the unique personality of certain elements to controlling the speed of their reactions, and finally, to harnessing that chemistry to generate power, we've connected all the dots. And this whole journey leaves us with one final, big question for the future. Are technologies like the hydrogen fuel cell the answer to our energy needs?